Hello everyone. Today I'm Bharity Yakha, our second semester, having roll number 21NS0-224. I'm here to present my topic, circular loop. So let's start about what exactly is a circular loop. So, a circular loop is nothing but just a loop which is made up of large number of very small straight wires. A magnetic field is produced by an electric current flowing through a circular coil of wire. Each small section of current carrying wire contributes to magnetic field lines. So, at the center of the circular wire, field lines become straight and perpendicular to the plane of the coil as we have seen at this picture or diagram. Right hand thumb rule is also used in this circular coil, which also that is when we hold a straight current carrying wire in our right hand in such a way that the thumb indicates the direction of the current and the remaining fingers determines the direction of the magnetic field. Then we can, using the right hand thumb rule in the diagram, we can also see that when the current is inward, when upwards, the magnetic field lines go in an anti-clockwise direction, and as the current moves downwards, the magnetic fields move in clockwise direction. Also, the magnetic field around the straight current carrying conductor or wire can be increased by bending into circular loop. So let's start our introduction. These are some things related to circular loop. Exactly, magnetic field lines in the current carrying circular loop. We know that the magnetic field lines have a circular pattern when an electric current is passed through a straight wire. However, when a wire is bent into circular loop and an electric current is passed through it, the nature of the magnetic lines changes as shown in the illustration, as in this figure 2. We can also see that the magnetic field lines near the current carrying circular loop form concentric circles, meaning circles, and in the middle part of the circular loop, it also seems to be perpendicular or straight. It just looks like it's straight, but it's actually perpendicular to the circular loop. As in this figure, let's see the left side figure. The magnetic field lines due to circular loop carrying conductor. Here, right hand thumb rule is used when the current is upwards, the magnetic field lines move in an anti-clockwise direction, and when the current is downwards, the magnetic field lines move in clockwise direction, and the middle part of the magnetic field appears to be perpendicular to the circular loop when current is passed through the circular loop. And in the right hand side, a small demonstration is done of right hand thumb rule, that is electric current through a wire, straight current carrying wire, and the direction of the magnetic field is determined by the thumb and the remaining fingers respectively, which creates a magnetic field around the wire. Direction of the field by right hand thumb rule can be determined like the diagram on the right hand side. Suppose, let's talk about an experiment related to circular loop. Suppose we take a circular coil with multiple turns, place it halfway through the sheet of cardboard and connect it in series with the emitter, battery, plug key and a rheostat. Now sprinkle some iron fillings over the cardboard and pass an electric current through the wire by switching on the plug key. The iron fillings present on the cardboard will align in a specific pattern, proving the presence of the magnetic field. As you can see, the experiment I talked about determines the presence of magnetic field in presence of rheostat, plug key, battery, ammeter, and a circular coil bounded half on the cardboard. When current is passed when plug key is on and using battery and the ammeter, when the current passes to the circular coil which is on board on the cardboard, we can see that the magnetic field lines near the coil are concentric circles at both the sides going upwards and downwards current, and the middle part of the circular coil, the magnetic field lines are straight. So as you can see, it's just the iron filings through which current is passed, and the concentrics and the magnetic fields are determined. Thus, using this experiment, we can determine the presence of magnetic field. So now we have reached till the part of the derivative part, which is a famous expression of magnetic field on the axis of current carrying circular loop. So let's see at this picture. Consider a circular loop C carrying current I. The radius of the circular loop is A and the distance of point P from origin O is X, and from the current element we have considered a small current carrying element IDL, and the radius and the distance from this current element to the point P is R. Here the magnetic field at point P due to the circular loop is to be calculated. Now we all get a common question that which component will be responsible for the magnetic field on point P due to the circular loop. So looking carefully at this figure, we can see that the sine component are getting cancelled while the cos component are in the same direction. So hence the cos component will be responsible for the magnetic field on point P due to the circular loop. So we are now about to calculate the magnetic field on point P. Using the dBx component, that is x-axis, we will calculate dB cos theta, which is the cos component. From the Biot-Savart's law, we all know that dB will be nu naught IDL cos pi by 4 pi r square, where I is the current flowing through the circular loop. dl is a small element taken from the circular loop. Cos phi is the angle between the current element and the point P, forming triangle, and the r square is the square of the distance between the current element and the point P. Further calculating, we have to find the cos phi, value of cos phi. From the triangle OAP using trigonometric identities, cos phi will be base by hypotenuse, as we all know, that will be a by r square. Again, using Pythagoras theorem, we can find the value of r, which will be root under a square plus x square. That is, now putting the value of cos phi, we get a by r. By further calculating, it becomes dBx equals to nu naught Ia dl by 4 pi r cube. Since we have only taken a small part or a small current element, now we have to further calculate the entire value, that is the entire magnetic field on the point P due to the circular loop. Therefore, to calculate the total magnetic field, we have to integrate dBx. Therefore, by integrating, it becomes B equals to integration of dB, that is put in the value of dB, we get nu naught Ia dl by 4 pi r cube. Here, nu naught Ia by 4 pi r cube is considered as constant, thus they are outside the integration. And by integrating dl from 0 to 2 pi a, where 2 pi a is the circumference or the total limit of the circular loop, as it is a circular loop. Thus by further calculating, we get nu naught Ia 2 pi a by 4 pi r cube. Now moving on to the next part, we get B equals to nu naught I 2 pi a squared by 4 pi r cube, which implies nu naught I a squared by 2 a squared plus x squared 3 by to the power 3 by 2. Here putting the value of r, we get this equation. Therefore, the magnetic field on point P, which is a circular loop, will become B equals to nu naught I a square by 2a square plus x square 3 by 2. Further, there is also the equation of magnetic field at the center of the circular loop. That will be, when the point is at center, x will become 0. Therefore, by putting x equals to 0 in the above equation, we get B equals to nu naught I a square by 2a cube, which implies B equals to nu naught I by 2a. Here we have taken the number of turns as only 1, but when we have n number of turns, we can multiply the equation, both the equation with n for n number of turns in circular loop. Moving on to the next. As a result, there are few factors where magnetic field depends on the circular loop. First, the amount of current through wire. If the current is increased, then deflection of needle of the magnetic compass inside wire will also increase. Strength of magnetic field is directly proportional to current. That is, more the current, more will be the magnetic field. Second, radius of circular wire. Strength of magnetic field is inversely proportional to the radius of the circular wire, as I told earlier. Deflection of the needle of magnetic compass placed at the center of the circular wire of smaller radius is more than placed of circular wire or larger radius. That is, as I said earlier, the magnetic field lines near the current carrying circular loop will form concentric circles, and the magnetic field farther from the circular loop will appear to be perpendicular to the circular loop. Also, the number of turns in circular wire. If number of turns in circular wire are increased, magnetic field at the center of loop also increases. That is, more the number of turns in circular loop, the more will be the magnetic field. The more magnetic field will be generated. Next, the magnetic field. Also, some of the factors. The magnetic field. These are just the same. That is, first one, more the intensity of the current, more will be the intensity of magnetic field. The smaller the radii, the more circular magnetic field will be generated, and farther the magnetic field, straight it will appear. And the number of loop in the circular loop will also determine the intensity of magnetic field. Lastly, we found that the magnetic field lines near the current carrying circular loop from the pattern of concentric circles, while the fields farther from the circular loop are perpendicular or appear to be straight, as I told earlier. When an electric current is passed through a current carrying circular loop, the magnetic field lines are generated in a circular pattern around the arms of the coil, while the magnetic field lines are straight at the center of the loop. Seeing the diagram, we can also understand the direction of the current element, whereas I didn't mention that though. It also depends on the right hand thumb rule. Moving on to the next. The intensity of the magnetic field is maximum at the center of the loop and decreases upon moving away from it. That is, the magnetic field near the loop is the highest and it decreases upon moving away from the loop. The magnetic field intensity decreases with an increase in the radius of the circular loop. That is, they are inversely proportional to each other. The magnetic field intensity increases with the increase in electric current which passes through the circular wire loop. The magnetic field intensity increases with an increase in electric current which passes through the circular wire loop. The more the intensity of magnetic field, the more that implies the current is maximum at that point. Lastly, I would like to thank Mr. CP sir and the whole HOD department for giving me this exciting topic. To be frank, I didn't get much problem while discussing this topic. At first, I just said only how to make presentation on only the topic circular loop, but as I gone deeper and deeper into this concept, it was really so exciting, and I didn't got to know which and I also had the experience on this topic which I had never known in my earlier sessions or classes, in my earlier classes. So thank you so much, our whole physics department, and I am very thankful to the whole physics department, especially CP sir, Sobat sir, and Nobu sir. Thank you so much. This is all for today, and thank you for listening all.